Thank you. Let me start by saying what a joy it is to be here and to meet all these old friends, perfumers and perfumer chemists like Roger, who's trying to act natural here in front of me, who, when I was a callow youth of 43, taught me really almost everything that got me started into this business, because as many of you well know, it's not easy to gather information about fragrance from the outside. There's an awful lot of folklore and unwritten stuff that you have to basically talk to people. So if you can pick up the phone and ask Roger, everything becomes magically easy. And that was what happened. And I'm very grateful to your help over the years and to your support also, because, you know, as you probably know, I am a proponent of a theory which has long been considered controversial. I'm not sure what the word controversy actually means in science. Mostly it means people totally ignore you. So you spend half your life wishing for there to be an actual controversy so that you could get a word in. And then when it finally happens, which is now actually, and I'll show you some evidence of that, it's basically over because it means people are no longer able to ignore you. So many of you know me actually not at all as a scientist, but as the author of this is the first book that I wrote in French in 92, 94. And I just sat down and started writing. I was in my mother's house in Paris. And when I gave her the first few pages, she said, "I had no idea you could do this." But she said it in a way that suggested this was really alarming, you know? There's something deeply wrong with me. Anyway, so I wrote this book, and it was the best-selling guide to perfume in France because it was the only one. So they sold probably 58 copies, but there was no... So you can say, honestly, it was the best-selling guide. And then many years later, together with my wife, Tanya Sanchez, can we lower the lights just a little bit? We wrote a much longer, the first one had 200 fragrances, this one 2,000. And we wrote this guide. I had an absolutely fantastic time doing it, just before practically every fragrance was reformulated. So do not trust what it says in there, because you're going to buy something that has nothing to do with the original. One of the wonderful things about writing a perfume guide is you get this kind of stuff happening when you give a lecture at the BSB. So I don't know if Lisa Luneva is in the audience, but okay. But you know, I can tell you this does not happen in science. Okay? So I warmly recommend going into the arts. And some of you know me in part through this work that we did with Flexitrol, where for about 8-9 years we created a lot of molecules, and then like 9 startups out of 10 we went bust. But we created an awful lot of intellectual property, and this is, I just want to emphasize, all this IP was created with only one chemist, one full-time chemist, okay? Because we had computational abilities to predict odor. We used very few chemists, which is why we were unpopular with chemists. And my favorite molecule, this is a shameless plug, as they call it, is this molecule, which is basically hydroxycitronellal, but 25 times more powerful. And the patent is still there, and we accept credit cards. So now, from all this serious stuff, let's move on to frivolous things like science. And let me just explain a little bit about what I'm going to be talking about. So the sense of smell is really mediated by the only part of your brain which is exposed to the outside air under normal circumstances. And the neurons, as you can see, the olfactory bulb, which is that sort of thing there. Do I have a pointer? Yeah, I do. Okay. So this guy is quite a big chunk of brain and has these groups of cells called glomeruli, and the neurons grow through a bone, which has conveniently placed holes in it. And sometimes it's absent. Do not put things up your nose, because some people have a malformation. There is no bone, and the pencil will go right up into your brain. Not a great idea. And then these cells have cilia that are in the mucus, but basically exposed to air. And the cilia have these proteins in the actual membrane, which are the receptors. And the whole story of tonight, and the whole story of the last 20 years of my scientific life, is what is it that these dudes actually feel? What do they recognize in an odorant? I mean, there's plenty of mysteries in all the senses. It's not like as if we understand vision perfectly or hearing or anything, but in olfaction, to my mind, the greatest mystery is how is odor written into a molecule? What is it that these little guys, receptors, feel? And most of olfaction occurs between these two size scales. Dimethyl sulfide is not the smallest odorant, but it's pretty small. And musky-tone is pretty big. And in between lies everything that perfumers use on a daily basis in terms of numbers of carbons. And that's hundreds of thousands of molecules that have been made by all the various companies or purified from naturals. And that some of them have become materials, some haven't. They're sitting on the shelf of a company. Now, the standard explanation for how smell works is shown here. You have a, can we actually lower just the lights just a little bit more? Because the slides look better when. Okay, that's good, yeah, thank you, that's perfect. So what happens here is a molecule comes down and some groups on the protein, here a benzene ring and a hydroxyl ring, attached to it like magnets, so to speak. There are some attractive forces that bring them together, and the forces cause the protein to change shape. So it is the interaction of the molecule with the protein that when you put it in, it's like a magnet. The protein goes click and is turned on. This is the standard explanation for how odor works. And one of the consequences of it, when Linda Buck and Richard Axel discovered the receptors in '91, they discovered that there were 400 or 500 receptors, different receptors in the nose of humans, 1,000 in the mouse, 64 in fruit flies, but basically lots. And so this is the response of, you have 15, I think, receptors here, and some, I don't know, 20 different odorants, and you find out which receptor responds to which odorant. And what happens is that some receptors respond to a lot of odorants, like, some odorants stimulate a lot of receptors, like this guy, and some odorants stimulate only one. And you can easily imagine that this forms a sort of a binary code, with the 1 being the receptor is turned on and 0 not turned on. And that makes a word. And if you do that for all the different receptors, you end up with different encoding of the different odorants. And if you have 400 receptors, you have basically covered all the bases. Because 2 to the 400 is several orders of magnitude more than the number of atoms in the entire universe. Okay, so you're cooking. Now, however, once you've said this, you're still unable to predict the smell of a molecule. You said, basically what you're saying is, surely there must be a way, because there are enough receptors to do the job. But you don't know which receptor is doing what, and which receptor is feeling which part, and so on. So it's an explanation, but it has no predictive value. Now, however, the effect this discovery and this concept has had on the field has been interesting, because until, I suppose, the end of the 90s, it was legitimate to wonder really how these receptors were feeling the odorants. And it became clear that there was no obvious pattern to anything much, and that until we knew the shape of each of the receptors, there was not much point in messing around with all these ideas. So basically, people came to the conclusion, they did what's known in military tactics as retreat and declare victory. Okay? Charles Sell, who is one of the most knowledgeable fragrance chemists around, has written many articles and several books, and his point of view is it's going to be some complicated function of all these receptors, and we cannot figure it out now because we don't have the means yet. That's why he entitled this thing On the Unpredictability of Odor. Now, however, those of us who are incurable optimists have cause to wonder whether this idea is right. And it goes back to a very old problem, which every chemist, who's an organic chemist here? Can you stick your hand up? Okay, a good profession. So all of you guys know that molecules have smells that correspond to their functional groups. So that if you have a nitrile, it smells nitrilic. If you have a sulfide, it smells sulfuraceous. And there are various others, like oximes have a very distinctive smell, and all this that are listed. This guy, Hein Klopping, is the fellow who discovered the benzothiazoles that prevent lemons from being covered in mold. So he's done a fantastic work. But he also had an interest, like many chemists, he had an interest in olfaction. And he pointed this out and said, look, basically this is very weird because each one of these little molecules can only make one bond, really, with whatever receptor. And how does the receptor know from that one bond whether it's an SH or a CN or an NOH or any damn thing? It just seems very strange. Incidentally, feel free to interrupt me. If there's something I say which just makes absolutely no sense, stick your hand up and ask. So let me give you the most beautiful example of this is, of course, OH and SH. OH, alcohols, SH, thiols. Alcohols never smell of rotten eggs at any concentration. And if they do, you know there's a problem, right? I mean, they give you vodka, it's 40%, you can go in there and there's no rotten egg smell. Conversely, SH always smells of rotten eggs at any concentration. That's very strange. What molecular mechanism can tell SH from OH with perfect precision? Because a friend of mine used to say, well, because he's a physicist, he said, well, that's easy. They're a different color. So just for him, I made the slide like this. Really. So at this point, you begin to see, actually, of course, molecules have a sort of an outer surface of electrons. And more than that, they're also moving around like mad at 300 Kelvin. They're jiggling. This is actual molecular dynamics simulations. You can see they're kind of moving around. So you can imagine they gave you these two molecular models in a little velvet bag, right? And you're on the tube, and you're supposed, with your hands, to figure out which is SH and which is OH. Forget it. Okay? This is what the receptor does unerringly, all day, every day. Okay? And we don't understand how. So when I got interested in this particular problem, I realized that there was an alternative theory of smell which had been propagated, first of all, rather tentatively by this man, William Ogle, a very pompous medic from the 1870s, but who used long Latin words. But he suggested that the sense of smell was akin to hearing. And then this man, Malcolm Dyson, who in this very room, I believe, in 1938, to a polite assembly like yours, proposed that we smelt the vibrations of molecules. Okay, and I'll explain in a minute what that actually means. And then this guy, Bob Wright, who incidentally, I think if there was a reference boffin, you know, together with the kilogram and the meter, Bob Wright would be there. Has anybody ever looked more like a scientist than Bob Wright? and Clifton Malone, who was an analytical chemist who got really cheesed off at the fact that his nose was better than any of his instruments and really tried to figure out how that worked. These are the people who all proposed over the years that the nose detected molecular vibrations. And so I came rather late to this party and was faced with the problem that all these theories had. This is an infrared spectrometer which measures molecular vibrations. And I'm in a position to reveal that when you look up somebody's nose, you see nothing resembling this at all. And so this had been the major problem of vibrational theory, is that people say, well, it's jolly good to say that that proteins measure vibrations, but how in God's name are they going to do it, right? There's no prisms, nothing. So this was the state of play when I got interested in this. But this is where the sound happens. Okay, so these are the frequency of vibration of the OH and the SH translated down into the audible range 10 to the 11 times, I think 10 to the 12 times. So you have a nice little, what is it, I think it's an augmented fourth or something. I was thinking, and indeed people had noticed that this vibration at 2650 was damned unusual. And in fact, nothing else seemed to have that particular vibrational frequency. And indeed, nothing else smelt of sulfur. In fact, nothing actually, except for what I'm going to show you now, smells of sulfur. So I started looking around at the time. I thought, before I get sucked into this crazy ass thing, let me try and convince myself that there is some truth to it. Let me find another thing that vibrates at the sulfur frequency and see if it smells of sulfur. And after rummaging around for months and months and months, I found this class of compounds, the boranes, that are extraordinarily perverse chemical creatures prone to spontaneous combustion and explosion and highly toxic. But I found one that did not blow up, did not kill you instantly. And you could order from Sigma, their supplier, and indeed 1 gram, and it came the next day, and I opened it, and it smelled like leak, okay? So an SH, a smell of sulfur. And I thought, okay, if this is a coincidence, I'm going to bet my life on this, okay? Because, and I thought this was amazing. And then I started researching the whole thing about boranes, and this is the man who really figured out all the boranes. They're evil molecules, they're hard to handle. And he got a Nobel Prize for this. And what does he say about the boranes, all of them? This is what, 1912, okay? They all smell of sulfur. They all have this vibration. So then I started talking to my inorganic chemist friends, and I said, of course boranes smell of sulfur. Why didn't you ask? And I was like, all right, why didn't you say? So that was the starting point, really. Now, I was sort of mulling this over when I came across this article that described a completely different way of doing spectroscopy. In other words, of measuring the vibrations of the molecule. Normally, when you want to measure the vibrations of a molecule with one of those devices I've shown, what you do is you shine light, infrared light as it happens, through the molecule, and you figure out which bits of the infrared are absorbed. When it's resonant with the vibrations, the light doesn't go through, okay? This was a description of an instrument which did exactly that without any light. It just did it with electricity. And being a biophysicist and interested in biological electronics, I thought, electricity, we can do that. We can't do light. It's extremely difficult to do infrared light with living systems. But electricity, we can. And just to explain what I mean by this, in every one of you, if you're still alive, listening to this lecture, has roughly between 75 and 100 amps of current, electron current, flowing through your cell in the body, 75 or 100. Most of it in the brain, under 1 volt, so there's about 100 watts. This is electron currents. We have 100 amps, so you can steal a few nanoamps to detect odorants quite easily, was my thought. And so I started working on this idea that actually we used an electron tunneling spectrometer. And I published, after much tribulation, this article in '96. So it's 20 years ago. So this is a big anniversary. And it was the only paper in Chemical Senses that ever had this above the text. I have no idea what that means about the other articles in Chemical Senses, but they put that for some reason. Now, let me explain these slides that I've made specially because I always did it by hand waving, and I thought, come on, make some slides. So the energy of a molecular vibration is the energy that it takes to compress the spring between, this is a molecule consisting of two atoms. So when you squeeze the spring, the energy goes up, because it's hard. The energy of the molecule goes up. And it's specific to that combination of masses and atoms. Now, if you have an electron, electrons are funny, sort of fuzzy creatures. If you have an electron traveling from left to right and there's a gap, the electron, if it were a purely classical creature, would simply bounce back. It would be like hitting a wall and bouncing back. But because it's a quantum creature, there's a probability that it feels that there's an empty state on the other side of the barrier. And what happens is it disappears on one side, it appears on the other side. And that's called tunneling. And this is called elastic tunneling, and there's no effect on vibrations. However, if you arrange things in this fashion, where you have one level on the left at a higher energy, another level on the right at a lower energy, and the difference between these two energies corresponds to the energy of the vibration, then what happens is this. The electron comes up, and it excites the vibration and appears on the other side. And it cannot do that if there's no molecule there, and it cannot do that if the molecule has the wrong vibration, because the thing has to just exactly add up. Is this roughly clear? Okay. So this is how a tunneling spectrometer works. And so I propose, and these are machines which can be built, in fact, and exist. So what I basically proposed was simply that, or simply is perhaps an overstatement, that the receptors contained this little device inside them, and that's how they measured the presence of odorants. And this was my original proposal. So I've done a little animation to show the electron jumps, excites the vibration, and travels, and turns on the receptor. Okay. So at that point, I was distracted from science by designing all these molecules whose patents I showed you earlier for about 8 years. And then when the company went south, I went back to science, and as it happened at the time, the DARPA, have you guys heard of DARPA? DARPA is the defense, they're the people who invented the internet. We should all be grateful. They're the Defense Advanced Research Projects Agency of the United States. They're just plain crazy. They basically sign checks for $50 million on the authority of one person without any committees getting in the way, which is like dying, going to heaven, okay? And they signed us an enormous check to study this idea and to test it. So what I did was I went at that point to Athens to work with Makis Skoulakis, who is one of the best geneticists of fruit flies and one of the best behaviorists of fruit flies at the same time. This guy is a genuine biologist. He actually knows biology. And we he always was working on the fruit fly, and the fruit fly is insanely great, okay? Now, I realize you guys aren't necessarily going to start working with fruit flies tomorrow morning, but I just want to do a sales pitch here. There's 14,000 genes, and we know all of them. You can block selectively any one of these 14,000 genes. You simply order the fly with that block gene from Vienna for 25 euros. It comes in the post in a little bottle. So if you have an idea, you can test it 2 weeks later for 25 bucks. I mean, come on. Well, I mean, what could possibly be more fun? 7-day life cycle, 75% match with human disease genes, and amazingly, a complete sharing of mutants among the community. If you publish a paper where you've made some weird-ass genetically engineered fly, once the paper is published, that very day you have to supply that fly to all the other scientists. No ifs, no buts, no nothing. If you don't, you're banned forever from civil society. So, and these guys have a good sense of smell. That's why they're called fruit flies or vinegar flies. That's why they end up when you have a nice holiday and you order a glass of nice Cabernet Sauvignon and you forget to drink and you look in there and there's like 20 flies got there first, okay? And they do that by smell. So what we decided to do was to test the theory with a very simple experiment, which is if you take a molecule of an odorant, in this case particularly octanol, and you replace all the hydrogens with heavy hydrogens. Hydrogen comes in several different flavors that differ in weight, but are very similar chemically. They have an extra neutron in the nucleus buried in there in the middle of the atom. So the heavy hydrogen has almost identical chemistry to normal hydrogen, but it's twice as heavy. And therefore, the spring between the atoms will be the same, but the mass is twice the mass. And so all the vibrations are shifted down. So you're going, mee, ooh. Okay? So if you I actually played with, I hate to admit this, but for months I was listening to musks on my computer. And I thought I could tell them apart from ambers. And then I did it blind and I couldn't. But the idea is quite simple. If indeed the nose smells molecular vibrations, then these two molecules, normal and deuterium octanol, should smell different. Do they? Well, to us humans, not obviously, but we tried it with flies. Okay, these are the spectra of these two molecules. So what you can see is that this is the frequency of the vibration from nothing to the highest vibration. This is OH, which is high. These are all the CH stretches. And when you replace with deuterium, you get CD stretch, and you can see there's a big shift in frequency, about 1 over square root of 2. So can flies tell these things apart? Well, it's actually a very simple thing to test. You take some flies and you drop them into with a little elevator in a thing, and they have two tubes coming in with two different odors, and they have to choose which way they go. So they go, think about it for a second, and then they go into one tube or the other. And then you just simply take the tubes out and count the flies. I mean, there's nothing simpler as an experiment. It's cheap, simple, effective. So they sort themselves out and you count them. So what you do is, the first thing we did was with acetophenone, which is a sort of Hawthorne type smell, we put them in a tube with air really on one side and acetophenone on the other side, and the flies go towards the acetophenone. They like it. It actually smells good to them, so they tend to go towards it. When you replace acetophenone has 8 hydrogens. That's the molecule. So it has 3 on the methyl group and 5 on the benzene ring. If you replace the three methyl hydrogens with deuterium, the flies are less attracted to it, but not significantly different statistically. If you put 5 deuteriums, they start saying, I don't like this. Okay, and they go the other way. And if you put 8, they definitely don't like it. Okay? This is interesting. Now, naturally, when you show this to a chemist, he says, my good man, these different isotopes have different impurities in them. And they, as you well know, all the perfumers here know that one batch of whatever, aldehyde C10 smells different from the next one because of impurities. So maybe they're reacting to impurities and not to the deuterium. So what we did was, we decided to ask the question, first of all, we decided to train them to avoid things. So what you do is, this is where it gets really fun, is 90 volts in their little feet. And you ask the question, is deuterium really like a nitrile to them? In other words, can they tell the presence of deuterium, this CD stretch frequency, in any molecule? You know, is it something that transfers from one molecule to another? So what we did is we trained them to avoid, let's say, deuterated octanol, and then we tested them with deuterated or non-deuterated benzaldehyde to see if they could tell that there was deuterium in the benzaldehyde. This is transfer. And first of all, you can train them to avoid one or the other of the octanols, okay? They can avoid the H or they can avoid the D if you shock them to the appropriate one. But then you can do what I've just described, which is transfer from deuterium to deuterium. So you shock them against octanol, and they avoid benzaldehyde. You shock them against D-octanol, and they avoid D-benzaldehyde. All right? So now we're talking, because impurities becomes hard to understand unless there's an amazing coincidence between the impurities of two completely unrelated chemicals. But then we got really cocky. And we thought, after all, these flies are brilliant. So why don't we just give them a really hard test? Now, it's such a pleasure to talk to perfumers because I don't need to explain what these two molecules smell like to you, because you know already, okay? This is lemon-ish, and this is metallic lemon-ish. Is this actually still used in perfumery? You're still allowed to use it? Okay. So what we did, what's interesting about the nitrile is the nitrile, the CN stretch, is exactly the same frequency as the deuterium. Okay? So we asked, can you confuse them? If you train them against deuterium, will they hate the nitrile? You know, this was a definitive experiment because at that point, it's not a question of deuterium being slightly different or some damn thing. They only have one thing in common, and that's the vibration. So we did the experiment, and when you train them, when spontaneously they have no preference to nitrile aldehyde. When you train them against normal octanol, they don't understand the question. They basically, there's CHs on both sides. They sort of sit there and say, what's your problem? But if you train them against D-octanol, they avoid the nitrile. Now, I remember when we did this experiment, and I described it to a friend of mine who's a very distinguished physical chemist, he said, okay, now you've got my attention, okay? This is actually something which is very hard to explain otherwise than with vibrations. So I'm just going to skip this slide and go to this one. We decided to do the same thing with humans, to see whether humans could smell isotopes, the presence of deuterium or not. And this thing had a long and rather troubled history because originally we tried it with the same molecule as the flies, the acetophenone, and there was no difference. And Simon Gain worked for like 2 years testing people with D and H acetophenone, and he was getting a very small signal, and he calculated if he did 11,000 experiments, it would be statistically significant, and at that point, he would be close to retirement finishing his thesis. So that wasn't productive. So what we did was we went to, the idea was very simple. We went to the largest molecule we could think of, lots of hydrogens, on the understanding that the signal would be bigger if you replaced 28 H's with 28 D's than 8 H's with 8 D's, okay? So we used musks. And the interesting thing about musks, of course, as you all know, is how many people here have a musk anosmia, an anosmia to one musk or another? I'm sure you all do. You don't know, right? Okay. Most people will be completely anosmic. They will not smell one or more of the common musks. What that means is that there's only 1 or 2 receptors for those musks, so that a single mutation can wipe out your musk sensitivity, okay? And the reason is that these molecules are so big that they're close to the maximum size that the olfactory system can smell. And so if you imagine the curve, you know, how many receptors are there that can smell something? Well, the curve will go something like this. It'll go up as you increase the number of carbons because they dissolve in fats, and then when you get to 18 carbons, there's 0 receptors because anything bigger than 18 carbons has no smell whatsoever. Okay? So we decided to look at musks for these 2 reasons. 1, lots of hydrogens, and 2, very few receptors. And what we did was we took this beautiful molecule, exaltone, and we deuterated it with a very, very mild deuteration method. It's a rhodium catalyst, which just takes the hydrogens out and replaces them with deuterium, basically. And it's a wonderful thing because it occurs even almost at room temperature if you're patient enough. So you don't mess with the molecule. So you buy the best stuff from Firmenich, and you treat it gently. And you go for lunch and you come back and it's at 99% deuterated. It's absolutely amazing. And so then what you do is you do the gas chromatography mass spectrometry of this, and you find that in the peak there are various amounts of deuteration, so that the leading edge of the peak is the fully deuterated, the middle is 26 out of 28, and then there's the trailing edge is 18. And of course, it's actually really weird because this molecule is heavier than the H, but it comes out first from the gas chromatograph. So, do they smell different? So this was actually one of the great moments of my existence, right? So they did this in this company called Vioril, which is Greece's only fragrance company. And the chemist called me up to go there, and he hadn't opened it. And it was really do or die, okay? So we're sitting there. I'm trying to act not nervous, but not succeeding. And Cleo Magnati, who was a grad student whose project it was, and the chemist are there, and they open the little bottle of the deuterated musk, and it smelled completely different. So different that when we tested it on just ordinary and untrained, I mean, except for Cleo KM, who did 17 out of 17 blind, and myself, I did 12 out of 12. All the others were completely untrained people. And basically, it was easy to tell them apart. So the combined probability of this being a random event is negligible. So basically, the musks smell different. What do they smell of? It's very interesting. The deuterated musk has no musk character. It smells kind of like hot metal. So you have a molecule which is identical in shape, different in vibrations, completely different smell. So this is very exciting. And I'll show you, this is the face that Cleo made when she opened the bottle. I was actually there ready with my camera. And there she is, grinning from ear to ear, because this is amazing. I mean, it's just extraordinary. And this is Simon and Ian Smith, who did the experiment with GC Pure samples. So, why do these molecules smell of a musk? Well, it's very simple. They attach to one receptor. That receptor feels one vibrational band, because that's the way the thing is supposed to work. And that vibrational band is very likely this guy, the 1400 wave numbers. So the reason that musks all smell kind of the same is that they're monochromatic. It's the nearest thing, together with, let's say, SH, to a monochromatic smell that you'll ever have. That is the smell of 1400. And why are nitro musks so damned good at it? Well, it's very simple. The CH2 WAG, which is the vibration that we're talking about, corresponds exactly to the nitro stretch, which is a very potent vibrations in terms of, because it has a lot of charge on the atoms. So that's why nitro musks are musks. They were discovered accidentally by some dude who was making explosives. And he made this stuff which refused to blow up, but smelled great. And being a keen businessman, he changed the name of his business to, from explosions to fragrances. So all this time, the standard shape theory was simmering in the background, and the people were studiously ignoring all this work. Despite the fact that a lot of people found it interesting, the big panjandrums of olfaction thought we were simply crazy. Part of the reason they think we're crazy is because they're biologists, they don't understand any chemistry or any physics. So explaining a physicochemical theory to a pure molecular biologist is very much an uphill struggle. Now, you will have noticed that all the experiments so far are purely behavioral. You know, do the flies do this or that, or do the people smell this or that? And there's a weird thing about olfaction, which you may have noticed, which is that whereas people trust their sense of vision, if I showed you a visual illusion, you know, I said, take a look at this, you know, this red square looks a bit greener or whatever, you'd say, yeah, it does or it doesn't. But if you take an audience of scientists and you show them a smelling strip, first of all, they titter. They think it's hilariously funny that you should. These people who work on olfaction never smell their stuff, ever. They think it's ridiculous. Okay? So that the nature, the solidity, the importance of sensation is practically nil as far as they're concerned. So they're going around saying, who cares whether the flies go left or right? Who cares what the thing smells of? It's not important. We have to measure what's happening in the cells. And in part, I agree, we have to. But I still think that it's very important to figure out the sensation first. So what they went, these guys, Eric Bloch is one of the greatest sulfur chemists alive. What they did was they put the smell receptors in completely different cells. They took the actual RNA, the genetic message, put it in a different cell, kidney cells, and then put odorants on them to see if they responded. And they found that there was not much difference, statistical difference, between deuterium and normal odorants. And they published this enormously pompous paper, Implausibility of the Vibrational Theory of Olfaction, based on a negative result. I can get negative results anytime. You just do the experiment badly, and I guarantee you they come out negative. And so we got a little pissed off, and we replied with this. And the interesting part of this was that they claimed that our difference in smell with the deuterated musk was due to impurities. And they claimed to have ultra-pure deuterated and non-deuterated musk. So we simply asked them, do they smell different? And they refused to answer. They said that would mean nothing, so we're not going to say. They're like, really? It means nothing? Which planet do you guys live on? Anyway, so that was the state of play last year. And then a very eminent scientist, a very good molecular biologist, and perhaps the person who's done the most genetics work on olfaction in insects, who really wanted us to basically drop dead, actually wrote an editorial in PNAS, which is very rare, entitled Laying a Controversial Theory to Rest, on the basis of one negative result, nota bene, which is a little ambitious. This caused quite a ruckus, because a lot of people felt you're using a really big hammer on what you pretend is a very small fly, right? There's something wrong here. They're protesting too much. So a lot of people got interested in this over the last few years because of the controversy. And I just want to finish off. There's only 2 or 3 more slides. I want to show you what's actually going on right now. And this paper will come out in 2 weeks' time in Nature Scientific Reports. And it's done by Albrecht Haase, who is a quantum optics man, a real proper physicist who knows about quantum optics. And he decided, when he moved to Trento to follow his wife, who's a theoretician, he said, I want to figure out this olfaction thing because it sounds interesting. And he built an imaging setup to find out what's going on in the brain of the insect. And it's amazing, he succeeded. I mean, he had no experience of anything in that field. And I'm going to show you a trace. So this is the brain of a bee. Now, bees are the sort of Einsteins of the insect world. You know, they have enormous brains compared to flies. The fly brain would be about this size. This is the bee brain, they're gigantic. And they're geniuses, okay? And of course, you may have noticed we have the same taste as bees, right? I mean, we like roses, they like roses. Right? Anytime you go and smell a rose, there's a bee in there, right? So how do the actual brain cells respond to odorants? So what you do is you measure the response. Hang on. So these are the 2 guys, Albrecht Haase and Marco Paoli, who did most of the work. So they measure the response of the cells in the little lobe of the brain that is connected to a particular receptor. So this This clump of cells here is connected to one receptor, and this clump of cells is connected to another receptor, and they measure what's going on in those two things, an optical signal, which tells you what the receptors are responding to. Now let me show you the trace. So they put a puff of an H odorant, and both the green and red go up, okay? Now they put a puff of a deodorant, and one goes up and one goes down, okay? And now I rest my case. This is going to be really, really hard to explain any other way. And in fact, when you look at the whole picture of all the different glomeruli, the blue ones are going down with octanol, let's say. The red ones are going up. And if you do it with benzaldehyde, you get a different picture. And if you do it with acetophenone, you get a different picture. And if you do it with isopropanol, you get a different picture. So this paper will come out in 2 weeks' time. And I think will, in my opinion, will be, it's not the definitive answer, but it's certainly a watershed in this whole game. Now, the person who wrote that PNAS editorial is Leslie Vosshol, who's as I said, a very good scientist, but she's fond of saying crazy things. Now, I'd rather be a beast of legend than a beast of burden. And the next slide says why. Thank you very much for your attention.
Questions?
Thank you, Luca, for a very interesting lecture. I've got one question. You're talking about the smell as it goes up the nose and how the information transfers into the brain. What work's being done on the interpretation of that information?
It's very, very difficult to do. I mean, smell has been neglected, really, compared to the other senses, because you cannot, in the visual system, you can generate almost any pattern with a computer in 5 seconds of programming. And in the auditory system, the same thing. With smells, you're tied to molecules. And so you're always hamstrung by the fact, is there a molecule that will do this or is there a molecule that will do that? And the reason you're tied to molecules is that when you try to stimulate the actual olfactory epithelium, which people have done, nothing happens. See, this is very, very strange. If you stimulate the retina electrically, you get a phosphine in the visual field. If you stimulate the ear electrically, you get a click, and now you have cochlear implants that actually do this. If you stimulate the nose, nothing. And nobody knows what peculiarity of the cells or the electrical circuitry or whatever is responsible for this. But until somebody manages to put a suction electrode up the nose and stimulate the epithelium directly, we're stuck.
So it's still a black art?
Yes, it's going to be a black. I think black is very popular in the perfume world, right? So, yes, I think black art would be a great name for a fragrance. I think.
Okay, I've listened to you and found that very convincing. And I remember on a previous occasion, one of these listening to Charles Searle being equally convincing. And it
no, not equally. Slightly less.
Almost as convincing.
Exactly. Yeah.
Almost as convincing. I'm neither a chemist nor a physicist. I'm just an intelligent amateur, and I just look at the evidence, and I'm not sure what seems more convincing. So I wonder whether it's possible that actually our olfactory system can do both. It can detect shape and vibration.
Oh, I think that's totally possible. I don't think there's a major problem with that at all. I certainly have never claimed that this was the exclusive mechanism. I think, evolution does whatever it wants. If it needs shape, Bingo. And in fact, if you look at insect pheromones, I mean, the way I think about it is this, and it's not an original way of thinking, it's just self-evident. If you have a situation in which you know what molecule is going to come, in other words, the hormone from the female insect or something like that, what you want is a receptor that responds to that and nothing else. Yeah. So use shape by all means, okay? Yeah. If, however, you want a system that will respond in some way or other to a molecule that Roger has just made in his lab and that is never seen before, then if you use shape too much, it'll never work.
Sure.
Okay, so I think these are two extremes, and I have no idea where the actual system sits. But what Charles Sell says is there's not this. He says it's not vibration. It's different.
Sure.
Okay.
That was why I asked the question.
Yeah.
Thanks.
Thank you very much. Professor Turin, my name is Joseph from Alpha Labs London. Thinking about what you said about the vibrational theory and also about molecular shape, bearing in mind molecular shape and the chirality of molecules and the vibrational theory that you're positing there, could you offer any pitfalls that you can think of if we try to digitize olfaction?
Well, the principal pitfall is what we just discussed, that if you cannot stimulate individually, if you have no means of individual control of the peripheral receptors, it's going to be jolly difficult to digitize, because what are you digitizing? You can't digitize a molecule. The molecule is a molecule. So if your only stimulus is going to be something in a jar that has to evaporate, then you don't have enough grip on the thing to actually digitize it. To give you a counterexample to this, when you do magnetic stimulation of the visual cortex, transcranial, meaning you put magnetic pulses to stimulate visual sensitive neurons, you can get an image if you work your butt off and put lots of magnets and so on. You can get a rudimentary image. You can literally restore a form of sight to completely blind people, okay? But it's only because you can stimulate it. Now, colleagues, have been unable to stimulate the olfactory system at both ends, neither at the front end nor in the cortex. So we're not there yet. But thanks for giving me the literature, by the way, Joseph. I read it with great interest. It was great. Thank you.
Does the vibrational theory satisfactorily explain enantiomeric differences?
Thank you. That's a very good question. Thank you. So, as you well know, the majority of enantiomers have identical smells. In fact, it took a long time to establish the very first one that did not. The carvones were the first one. So, and it's important to bear in mind that a shape theory of receptors cannot explain those that have identical smells, because the receptors are always going to have handedness, and therefore the majority of enantiomers smelling identical is a major problem for shape-based theories. However, what's interesting is that the enantiomers will bind differently, of course, to receptors. And therefore, you'd expect them in a vibrational theory to smell somewhat different, simply because you're going to be binding more to one particular wavelength than to another. So this bugbear, many biologists chiefly say, well, the vibrational theory of smell must be wrong because it doesn't account for the different smells of enantiomers. It's not true. In a solid state spectroscope, which is what this is, if you take a crystal of a molecule and you measure its spectrum, if you align the crystal in the same way, the two enantiomers will have different spectra because of the relative alignment of the chemical groups. So this is a solid state spectroscope behaves differently. It's not isotropic.
Okay.
I apologize. I've just moved to Athens last week, so it was a pandemonium. And I was going to bring you a small sample of the deuterated musk. And then in the mess, I totally forgot. But what I was planning to do was to actually make a batch, a 10-gram batch, and make it available upon request to people who want to smell them. So we'll send 2 smelling strips dipped in a 1% solution, and you can smell it to your heart's content.
Yoo-hoo.
Yeah. No, but you know what? It's really funny because you guys would be impressed by the, but the ordinary olfaction scientist, so what?
But you have to convince perfumers, no?
No, perfumers don't matter. I'm joking. What I'd like you guys to do is to go and see your friendly neighborhood Swiss chemist and shake them and see what falls out. Because I suspect, I mean, my guess would be, if I had to guess, who's the smartest company in the business? Firmenich, okay? They've read this paper. I'll bet you they've made this stuff. It's a piece of cake, it's a day's work. I'll bet you they smelt it, and I bet you they know that it's correct, and I'll bet you they're not telling anybody. But eventually, the trouble with science is that everything happens on a scale which is comparable to a human life. Okay, so at my age, you want to rush Firmenich.
No, I don't want.
I'll do this. Press me, John. Sorry. Oh, sorry.
Yeah, thank you. Very good talk. The difference is, for me, is that... sorry. The difference is... Oh, sorry. The difference is that when Charles was talking, at his talk that we had with him, most of the molecules that he was talking about were relatively in the middle range of volatility. You're dealing with materials or molecules that are very small, relatively small,
yes.
acetophenone, benzaldehyde, and also then up into the musks.
Yeah.
I think I did smell those musks with Simon.
Yep.
To smell the things. The problem is, for me, is how do you make a batch of these products that's pure, that you know is pure enough?
Yes.
Because, sorry, but Charles Sell's law we used to work on was the fact that if you dipped a sample, then you would leave it for a certain length of time just to see how it develops over a period of time. So you smell it after, and you dip it an hour, then you dip it 15 minutes before you smell it, and then you dip it right at the end. I can see your smaller molecules are presumably much easier to get pure, to be sure that they're pure.
Okay, so what we did was we used a technique developed by Cristina Zilano in the US, which is it's basically a miniature version of GC preparation, okay? So you take a little Eppendorf tube, a little plastic tube, you coat it with Vaseline, and then you put it at the exit of the GC when the peak comes out. So when you hear the chart recorder going, you put it there, and when it gets to the top, you take it away, okay? And then you have the GC pure thing, and you close it. And that's good for one A/B test, GC pure.
Because before that, we used to use cotton wool, didn't we? I think we started with absorbing it onto cotton wool.
Yeah, the thing that we needed to do was to have those things prepared beforehand and sealed.
Oh, okay.
Okay, so that you'd make like 20 of these guys, and then the people would come and smell them, and then you'd make 20 more.
Right.
So we had GC pure material, and it was amazing because I was standing there over the GC, and when it came out from the splitter, it was just fantastically different. I mean, just no comparison.
When I first read your paper, I spent many hours in the GC tube in my time, and everything at that end smells burnt.
Yeah, no, I know. Columns smell burnt. No, but.
Did you do the sort of smell of the musk from, preparing in the same way?
Yeah. The thing smells burnt even in a liquid, even on a dipped paper. Burnt is.
Does the musk get
Yeah, we did a sham. Absolutely. We did the sham deuteration with H2O. We went right through the whole synthesis, sham synthesis. So we took a normal musk, and we replaced H with H. Okay, and then put it through the whole thing. Well, we've learned a lot over the years because the chemists always ask, pesky questions, and you have to answer them. And then when you finish with the chemists, you start with the physicists, and then with the perfumers, and then with the biologists, and then with the molecular biologists, and then you retire.
Sorry, hi. My chemistry is really far away, and I'm actually a perfumer, so I have a question about the enantiomers, because you were saying about, I guess, the positional ones, but what's about the optical ones?
No. Optical enantiomers. That's what we were talking about. Yeah.
Okay.
No. Not isomers, not stereoisomers. No, those smell different. They have different vibrations. Yeah.
Sorry, see, I told you.
Any more questions? Last one, anyone?
Joseph.
May I ask one more? Professor Turin, given what you were describing about quantum, do you think the perfume industry should take some lessons from that, or just carry on making juice?
I think carry on making juice is fine. I think first of all, much in the way that painting as an art does not depend very much on knowing the chemistry of alizarenes. In a way, some of the older perfumers that I know, like Guy Robert, the late Guy Robert, knew zero chemistry. I don't think he could have drawn C10-aldehyde. So he was a great perfumer. So it really doesn't matter, except in the general sense of curiosity. You might want to know, but it doesn't make any difference artistically, in my opinion, to anything. Now, to the research chemists, I don't really know, because you see, if you say, well, I want a material that smells like, we did these allergen replacements was our trade. So to remove the double bond, which is causing mayhem, but to maintain the same smell, that kind of stuff you can do with these methods. But to create new molecules in the end, I remember I went to Firmenich once, and their chief chemist said to me, look, what we do is we patent a process. With the process, we make 2,000 molecules. We find the ones that are interesting, and we produce those. Okay, so it's a completely different approach. They don't care about calculating smell. What they're calculating is cost. Because if these were drugs, if you look at drugs, for example, you buy a pill and Valium or something, the stuff is at $5,000, $10,000, $20,000 a kilo. Okay, you can do some pretty heroic chemistry for that kind of money. You can do a 7-stepper with 5% yield. Okay, in a fragrance, if you wanted to cost $30 a kilo, forget it. So I don't know, to be honest, what the impact of this kind of stuff in the long term on the perfume industry will be. Make juice.
Ernst Bow said, didn't he? The future of perfumery is in the hands of the chemists who are producing the molecules.
That's right, and it is.
1923.
And it is, and they've produced fantastic things. I smelled one tonight. What was it called? Amber.
Amber Extreme. Very good. Yeah.
Another monster roaming the earth. Anyway, thank you all for your time. Thank you.